Hello, everyone, and welcome to today's webinar about Dewesoft IMU devices. This will be a more hands-on webinar, so I will first go over some of the theory and basic what is an IMU device, which devices we have in Dewesoft and which ones we support, and what are some of the differences between them and where to use them. Then we'll go over some of the most common settings for the devices. Then I'll show you all the configuration inside the software and how to mount the devices on a vehicle. So that's why I have this nice toy handy here. And last, I'll show you how to use NTRIP for RTK. So this is RTK correction over network. And there are several free services in Europe that you can use. And I'll show you how to use this from a computer or from a mobile phone. So it's best that we start with the basics. What is actually an IMU? So IMU stands for Inertial Measurement Unit, and it basically consists of two types of sensors. Normally for positioning, we use only GPS devices, which gives out the position that we currently have, velocities and so on. And this gives us big stability over longer periods of time. So we can achieve relatively high accuracy. But there is a downside that if we don't have a really good reception, at least for satellites, we can quickly get into situations where we have no reception and then we don't know what is the position of the vehicle we are measuring. In that cases, we can help with the IMU devices. So IMU sensors get data from accelerometers, and then we integrate that acceleration into velocity. And with the second integration, we can get position out of that. So IMU sensors have really good short-term position or stability. But the problem is because of noise and because of other influences, over longer periods of time, they accumulate bigger errors. So if you use a combination of both, a GPS which has long-term stability and good positioning, and if we use during GPS blackouts or where we have really bad reception, data from accelerometers or IMU sensors, which have good stability over shorter periods of time, we can achieve at the end much higher overall position accuracy and stability of outputs. So we basically combine GPS sensors with IMU sensors. We put both of this into Kalman filters, which determine the error and better predict the output. And out of that, we then get a much better position, prediction, velocities, accelerations, and so on. So this is basically a combination of IMU and GPS sensors. And in Dewesoft, we have different devices. So we basically support, we have smaller basic devices, which is the IMU1 or the gyro one. As you can see, this is a really small device that can fit on the palm of the hand. And the benefit of this is that it can be really easily mounted in any vehicle. So we provide with this also a suction cup where you can just pop it on the vehicle or on the roof and immediately you can start measuring. We have two of these smaller devices. One is the gyro one and one is the IMU1. The difference between them is that the gyro one doesn't have a GPS receiver inside, so it's basically just an IMU device. It has accelerometers, gyroscopes, and magnetometers inside. And the IMU1 also has a GPS inside, so it's an actual IMU device. They have 100 Hertz output rate. And we also have then a higher grade device, which is the IMU2. and this is used for ADAS testing and other high performance tests. The difference is that IMU2 has dual antenna. This is used to get always the actual heading out of the device. So with IMU1, when we are stationary, we cannot know really accurately what is the orientation of the vehicle. Because we have a single antenna. With IMU2, we actually use two antennas. So one in the front of the vehicle, one in the back. And the secondary antenna then acts as a base station to the primary antenna. And we always know what is the actual orientation. So as soon as we turn them around, we always know what is the exact orientation, even when the vehicle is stationary with really high accuracy. So this is the biggest difference between the devices. Of course, the IMU2 has higher accuracy sensors, it has a higher output rate, and it also has an option to use RTK. So this is correction data from either from a base station to get 2 centimeter accuracy of the GPS. Here is one application example, how we can use the IMU2. So this is, for example, for ADAS testing, where we have 2 vehicles connected between each other with Wi-Fi. We have correction data from a base station to both units. So both vehicles have a computer with an S-box inside connected to an IMU2. IMU2 provides synchronization, all the data, position with 2 centimeter accuracy, and synchronization for the data that is transferred via Dewesoft net. So then in the end, we get all the data in one vehicle, which is perfectly synchronized from both vehicles with high accuracy. And together with that, we always know what is the exact orientation of the vehicle, even when it is stationary. So this is one benefit of using the IMU devices compared to standard GPS devices, where we get the heading only when we start moving from the information from the velocity. And we get also all the accelerations, rose, pitch, yaw, and so on from the device. So if we go through to the device settings, inside Dewesoft, we have different settings for the devices for IMU1, for IMU2, and there are some different recommendations that we use. So we have different vehicle profiles that we can use, and we have different settings for the receiver. If we go step by step, the internal GNSS enabled is just enabling the internal receiver. Otherwise, we get data only from the IMU sensors. The atmospheric altitude enabled helps to determine the accurate altitude from the device. So if we get only the data from the GPS, this is not so accurate. So all the devices have inside a pressure sensor to measure barometric pressure, and with the help of that, we can much more accurately determine the current height of the measured vehicle or of the sensor. Then we have a setting for velocity heading enabled. This is a setting that is mostly used on IMU1, which has only one antenna, and we cannot determine the actual orientation of the vehicle when it's stationary. So when we start driving, we can determine the heading from the velocity of the vehicle. And we can also enable reversing detection, and that means that we will detect when the vehicle is going in reverse. Otherwise, the sensor will start to correct the heading if we are actually going in reverse, and this is not specified inside, because it always tries to correct for for the error in position. Another setting that is possible with the IMU devices is motion analysis, and this is an artificial algorithm for ground vehicles when we lose the GPS reception. It then helps to determine what the position is, but this is usually used mostly just for vehicles. We have another setting also for magnetometers, and this is the determination of heading for stationary vehicles from the use of compass. So, but this is a setting that we don't recommend being used with vehicles because there's often some magnetic disturbance. And let's say the velocity heading will give you much better output of this, or especially if you have DS-IMU2, dual antenna option should be used, and it will always give out really accurate heading. Now let's switch over to Dewesoft to see the device inside the software. So this is the user interface for the IMU devices. We see the device that we have connected. At the moment, this is the IMU2. And then we have the channel list. So from status channels to the most basic outputs, to raw channels, and to some special channels that are available inside Dewesoft. With every setting that we make inside the plugin, for example, if we select the channels that we want to use, we click them to use, and we have to update the IMU device. This is needed to send the configuration to the device and to update which channels are actually being sent out from the device. Here we can, for example, see if the device is working properly. If we look at roll, as soon as we turn over the device, we can see it measures 90 degrees to one side or to the other side. So before we do the actual measurement, we also have to take care that we have the correct mounting of the sensor. At the moment, the antenna is mounted outside. But a typical mounting or configuration on the vehicle would be that we would mount the device somewhere close to the center of gravity. If we use the IMU2 or the IMU1, we would mount it close to the center of the vehicle or close to the wheels or center of the wheels. We have to be careful in which way we orientate the device. So all the devices have, on the device you have a coordinate system showing X, Y, and Z direction. On the device, X direction is always in the front, Y direction is on the right side, and Z direction is facing downwards. So you can always help yourself with the right hand rule. If we put it this way, so we have X, Y, and Z. We have X facing forwards, then we have Y direction going on the right, and Z direction going downwards. And we can always identify the axis this way. We also have the angles for roll, pitch, and heading. So roll is around the X axis, pitch is around the Y axis, and heading is around Z axis. Now, to know which direction is positive or negative, we can also help ourselves with the right hand. So we have direction of the vector, and we have the direction of rotation. So for example, for roll, we have X direction going in the front, so in the X direction, and we know that roll is actually in this direction would be then positive. So for heading, since we have heading pointing downwards in Z direction, we have roll, heading then clockwise direction. And this way we can then also manually adjust the offsets, or we can also select roll pitch alignment if we have steady behavior of the device and the device is completely stationary. So if the device is mounted straight, so with Z direction facing downwards, we can do the automatic roll pitch alignment. Otherwise, if the device would somehow have to be rotated around, then we would have to manually input the heading offset because the device cannot detect it automatically. And we can then do roll and pitch automatic alignment. Now, the second thing, when we finish with the alignment offsets, we need to define the antenna offsets. So that is the distance from the antenna to the unit. So for example, if we have the unit mounted at the back of the vehicle, and we mount the antenna on the roof, like so, we then need to measure in the X direction, what is the difference. So here we have the antenna mounted in front of the sensor, so we can input the X offset in positive direction. If we mount the sensor in the center line of the vehicle and the antenna also in the center line of the vehicle, then Y offset would be 0. And we only need to input also the Z offset. So if the antenna is higher than the unit, we have Z offset in negative direction. So these are the basic offsets that we have to input if we are using the IMU1 device. And the antenna should always be mounted so that it is at the highest possible point. If that's a vehicle or a truck, it should always be mounted on the roof, and on the truck, the antenna should never be mounted behind a high wall, because otherwise we'll then get really bad reflection or even multipath error from jumping of the signal or from reflection of the signal. And if we have some obstructions over the antenna, this can also reduce the quality of the signal, especially if the roof is metal. It's also not recommended to mount the antenna inside the vehicle near windows, because this also reduces the reception. So always try to mount the antenna outside of the vehicle. It's also better if the sensor and the antenna are mounted close together, if that is possible. Both the unit and the antenna are IP67 protected, so it's no problem to mount it outside even in bad weather. Now the second setting we have to do is for the dual antenna. And here we measure the offset from the secondary to the primary antenna. So if we have a vehicle and we have the primary antenna in the front, like so, and we have the secondary antenna in the rear, we then measure distance from the secondary to the primary antenna. And we also look at the direction of the vectors. So if the primary antenna is in the front, then the offset is in X positive direction. We usually try to mount them in the same line as the unit and as the front antenna, so we can have Y direction or Y offset 0. And for the Z offset, if they're mounted on a roof which is not straight, then we also need to look at the height difference from the antenna. So here in our case, the front antenna is a bit lower. That means that we have here offset in Z negative direction. So minus 10 centimeters, for example. And then would then give us the correct offset from the antennas. It is also possible to have the unit outside of the reference point of the vehicle, or mounted somewhere not in the center point of the vehicle where we want to measure, and we can artificially change that reference point. So we can create a new reference point, and we can get all the outputs calculated in that reference point of the vehicle. So for example, here, if we mount the sensor completely at the back side of the vehicle, and we want to measure at the center of the vehicle, we can simply create a new reference point, and we can say that we want to have the reference point 1 meter in front and 10 centimeters below our current sensor, and this will give us additional outputs, which are calculated from the actual position and in the new reference point. So we get all the accelerations, velocities, latitude, longitude, height, and body accelerations and slip angles for this output. And we can just enable them, and we have all the calculations already done inside. Now, the last point we have to do before we can do the actual measurement is to set sensor ranges. Here we have to be careful that we don't select a range that is too small, because once we go into overrange, then the sensor will go into saturation and it will not output the correct values until we reset it again. So we have to use the highest range that we think that we will not achieve. We also have different options for filters. And here you should select the vehicle that is closest to what you are measuring. This basically sets how the filters behave inside the device. And for example, if we're measuring a car, we can select a car and it will have the correct filters for car behavior. If we select a 3D aircraft, the sensor will know that it's also turning around. That it's completely turning around. With the car, for example, this is a bit limited, so we don't expect that the car will be rolling around in normal tests. So that's why the correct filters should be selected. And as I mentioned before, there are different settings that we can select. So internal GPS should always be enabled. It's also recommended to use atmospheric altitude enabled. Then there is a difference if we are using the IMU1 or IMU2 device. So if it's IMU1, we would calculate velocity from, we would calculate heading from the velocity vector. So we need to enable velocity heading. And we usually detect reverse if we are going in reverse. Motion analysis can help in some situations, but this is not a mandatory settings. So this is the recommendation for IMU1. If we are using IMU2 with dual antenna, we need to disable velocity heading and reversing detection, because this is anyway detected by the dual antenna or with the secondary antenna. Okay, as soon as we have these settings, we can go to measurement. We enabled all the basic channels, so we get all the positions, velocities, and so on. And when we go to measurement, we can create our own custom screens, for example, to see how the heading looks like, roll pitch heading. Let me just... Let's first check the synchronization settings. So we need to have the correct time source. With the IMU, we have several options to set timing modes. We have PPS sync or we have master clock. Now the difference between them is that the device always outputs PPS pulse, which is used for synchronization. And we can use that pulse to synchronize other devices like our series devices, 43s, and so on with the sync cable. Or we can also use the device to synchronize it for the device to give out the absolute clock, and then we can use it for synchronization for Dewesoft net. So in this case, we'll use just PPS sync with the time source from the computer. And here we can then see heading, roll, pitch. We can add additional channels for accelerations or for velocity measurement. If we want to synchronize other devices with Dewesoft, we need to set the device. So here we have now a series connected, and if we connect the sync cable, we need to change one setting here because the IMU device always sends out the PPS pulse, and if we have the time source configured as it is, it means that the series also sends out IRIC synchronization data, and this will then interfere with one another, and the IMU will show sensor failure because it's interfering with the PPS signal. So we need to set an external time source of GPS PPS and select GPS PPS. Then we can see that the series has PPS input from the IMU sensor. This way, series device then gets the synchronization from the IMU, and they are also perfectly synchronized together. There is also a third option if we are using Dewesoft net. Then we just need to switch to master clock. And that way, the IMU will then, or Dewesoft will then use the absolute time from the IMU, and we can actually synchronize then several systems together. Now, at the moment, the way we're using the IMU is just with normal reception, so it shows the mode as standalone. We can also increase the accuracy of the device, and we have two options. One is with using RTK data, and we also have an option to use OmniStar subscription. So this is a paid service where we get the correction data also through the satellite with higher accuracy than standard, but still not 2 centimeter accuracy. If you want to have absolutely the highest accuracy, then we can use correction from a base station. So here we have one base station set up that is sending the data through a radio frequency modem. We can just simply connect this modem, the second modem, to the IMU, which is receiving this data. See, as soon as I plug it in, we get RTK fixed. This means that we have 2 centimeter accuracy, or highest possible accuracy for this device. As soon as I unplug it or we lose any RTK reception, after a few seconds, it switches then back to standalone. So it means that we have lower accuracy and lower position accuracy than it otherwise would. So it switches to DGNSS fix. As soon as we get correction data again, we have first RTK float, which is not the highest accuracy, and RTK fix means that we have highest accuracy with actual RTK position data. There is also one option of using network position. So this is basically the same service that we have. There are three options for using this correction data over network. You can register on this website to receive your user account. Then we have a permanent station list where you can actually see the status of the nearest possible NTRIP servers. So here, for example, we can select the one in Graz or the one in Italy. When we have our user account, we just start the NTRIP client. Here we can connect just a simple USB to serial converter, select our NTRIP server, and immediately we would get correction data, which is free of charge. Also high accuracy from the nearest server. Now the availability of this, of course, depends on the region where you are. Europe has quite good coverage of most of the stations around, and this is more or less free service around here. Of course, if we have other servers where you have a subscription, you can also use this with the same client. And there is also an NTRIP client for Android. If you have then a Bluetooth serial receiver, you can connect it to the IMU device, just the same as the modem, and you can send correction data from your mobile phone. We also sell devices which accept the SIM card and then connect to the IMU to have NTRIP data in areas where you don't have a base station and you can use mobile data. So this is shortly all from my side about using the IMU, how to connect it, how to set it up, and what are some of the specialties. And I thank you for your attention, and you are welcome to view also the other recorded webinars on our YouTube channel.